Hello everyone. It's good to be back again at GopherCon again this year. And today, I'm here to tell you a story. But before that, let me introduce myself. My name is Mohit, and I work as a software engineer at 1-N, where we are primarily focused on site reliability and backend engineering. I not only love to explore the internals and nuances of languages, systems, and databases, but also that of coffee. I also do a couple of solo bike rides across the country every year. And this is a story which happened about a month ago. So a new developer joined us fresh out of college. Her name's Alka. And she reached out to me one day telling me, Mohit, how can I be a good developer? And this sent me into a flashback. So about 3 years ago, when I had joined 1-N, Chinmay, our co-founder, told me that we are all about writing clean and pragmatic code that scales well. And now it was my turn to set someone on the path of being a good developer. So I told her, why don't you attempt the 1BRC challenge? And she was like, what is 1BRC? I explained that 1BRC is a performance-oriented programming challenge that was introduced by Gunnar Morling back at the start of this year. And you have a file that contains a bunch of weather station data, which looks something like this. So each line has the city name and temperature separated by a semicolon. You've got to read this file, you've got to process it, and then print the results such a way that all the city names are present in alphabetical order, along with the minimum, the average, and the maximum temperature. You can't use any external libraries, and the goal is to do it as soon as possible. And yeah, I forgot to mention the caveat. The file contains 1 billion lines. Now, Alka had never seen even 100,000 lines before, let alone 1 billion lines. So her first question was, how is this going to help me become a good developer? I told her that a good developer is not only concerned with writing correct code, but also efficient code. If you care about the performance and efficiency of your application, if you care about what resources it takes, not only in terms of the hardware that it takes, but also in terms of dollars that it takes to run your program, if you care about the scalability of your application, I think you should definitely attempt this challenge. I don't know which word triggered something in her, but she definitely felt motivated. And I'll share that journey with you, where we improved the execution time of our program from 2 minutes 27 seconds to just under 10 seconds. So this was the first attempt that we did. She wrote a pretty simple and readable program, which read the file line by line using scanner. It split the line on the semicolon and passed the temperature as floating point number. We used internal map for doing deduplications and internal string sort for sorting the city name slice. She was not happy with the execution time, and she told me, why is it running so slow? So I told her that, why don't you profile your application and see for yourself? And she hasn't profiled before, so she learned just enough to instrument it into her code to gather the heap profile. Now, from all the data points that it showed, she was only able to make sense that it allocated about 45.5 gigabytes of data. Okay, so she came to me the next day again and told me that she remembers from her computer architecture classes that integer calculations are easier and hence much faster than floating point number calculations. So I told her the same thing again. Why don't you try and see for yourself? So she quickly changed the floating point parsing to integer parsing. And to her dismay, the program ran even slower. The execution time was 2 minutes and 52 seconds. Now this is weird because this was quite contrary to what we believed in. So what's the culprit? To find that out, we gathered the CPU profile. And turned out that this new line that we had introduced, strings.replace, was the problem for all the latency that we had introduced in the application. So whatever performance benefit we could have achieved because of switching from floating point to integer calculations were overshadowed by this particular line. So now that before that, moving further, I would like to give you a general guideline that whenever you face this problem of choosing between an integer point or floating point calculations, go with integers as default, unless you have to do some expensive steps to do that. Because most of the times, those expensive steps are going to negate any performance benefits that you see. And it is generally advisable that you benchmark your programs. You you benchmark once with the floating point calculations and again with the integer calculations, and then trying to find the perfect balance and what suits your program the best. At this point, we decided that instead of changing things here and there and hoping for a performance bump, we should break down the problem and optimize one step at a time. So the first step was reading. This is how we were reading our program initially, one line at a time as string. This small POC read the whole file, which was about 13 gigabytes in size, in 22.5 seconds. But we noticed something off with this. When we captured the heap profile for this, we saw that only 1 megabyte of memory was allocated for the whole program. Now, this seemed very fishy because the file size was very huge and we expected more allocations. So turned out that we were not capturing the value that was being returned by this scanner.txt. So initially we thought that the compiler did its magic and prevented this call altogether because you're not holding that value. But that was not the case because the CPU profile showed mentions of this text method. So we read about compiler optimizations a bit more and found out that a compiler always does conservative optimization so that it can guarantee the safety of your program always. What happened here is that since we were not holding the reference to that value, the Go's memory allocator did its optimization and it prevented fresh heap allocations. So in order to prevent that, we decided to use, So first before moving to the solution, we decided to capture this particular line, and we found that this is a correct program, by the way. This ran in about 40 seconds. This increased our runtime. This increased the number of allocations to 995 million, and it allocated about 15.5 gigabytes of data. Now, this definitely needed to be improved. So what we did is, we decided to read the file as byte arrays instead of reading it as string. By doing this, we were able to improve the execution time of just reading the file to 19 seconds. It allocated just one object and used about 1 megabyte of data. So now that we thought we had nailed the reading part, we moved to processing the whole file. So we changed the scanner.txt to scanner.bytes in our first implementation, and we saw an improvement in our execution time to 2 minutes and 12 seconds. Now, this is the first time that we saw some improvement in our execution time of our application. So I asked Alka, how do you plan to improve this further? And she said that when she benchmarked and profiled this current application, she saw that our parser is taking a lot of time. This parse float functionality was taking up most of the time, which meant that we had to write some custom solutions for that. So that's what we did. And here we are splitting the line on the semicolon, just like before. The first part is the string. Over here, we are trying to find the second part. If it contains a hyphen, which means it's a negative temperature. Here we are reading the whole number part of the temperature. And over here, we are reading the decimal part. So after all this, you get the temperature as an integer. We do all the calculations on integer, and in the very end, we divide by 10 and then print out the results. Now, all these fancy bit operations that you see are Alka's contribution, because she said that from her competitive programming journey, over there, it's a quite common knowledge that bit operations are faster than normal arithmetic operations that we do. And she even showed me some benchmarks to prove that. Even if it meant 1 nanosecond of improvement in one operation, multiply that with 1 billion times and you save a lot. So with that done, we converted our float parser to this custom parser. This improved our runtime to 1 minute and 51 seconds. But this custom parser allocated a huge amount of memory. If you see from this heap profile, this bytes.gensplit is single-handedly allocating 45 gigabytes of data. And by this time, we were aware that allocating and then deallocating this amount of memory takes up a lot of time. So this needed to be improved. Could we avoid this source of our problem? So we jumped into its implementation and saw that it uses a generic split function, which handles a lot of edge cases and scenarios which it didn't want. We just wanted the index of that semicolon. So we changed that line with index byte. Now, by doing a single line change, we were able to reduce the memory allocation from 54 gigabytes to just 9.2 gigabytes. And our runtime or execution time improved to 1 minute and 16 seconds. But still, when we profiled this change, we saw that our custom parser is taking approx 18% of the whole execution time, which we again wanted to improve further. And this was the only abstraction that we were using in that particular code. So naturally, we jumped into its implementation. And funny enough, there was no implementation for this. This was just a function header in Go's code. This means that Go uses low-level architecture-specific assembly language for index bytes implementation. And my intuition was that since the language itself is optimizing this function call so heavily to use assembly language directly, we can't optimize this further. But I don't know if Alka was feeling sleepy that day. She anyway changed this into a simple for loop. To my shock, this parser changed the runtime from 13.4 seconds. I'm talking just about the runtime of the parser for now. So it changed from 13.4 seconds to just 7.2 seconds. This is crazy. Believe me, because how can a simple for loop that has been existing since the caveman times beat all the performance improvements that Go has done throughout these years? So we studied a lot for this. We did a lot of benchmarks and then found out that a simple for loop is more efficient at finding things in smaller arrays than compared to these advanced SIMD implementations, which will prove to be beneficial in longer arrays. And since our individual lines in the file were very small, going with a for loop made much more sense. Now that we had practically modified every single bit of code, we wanted to make our program parallel. So we created a simple one reader and one worker model where we were reading. This is the reader's code where we are reading the line and then putting it onto the byte channel. Here the worker is reading from that byte channel, parsing each line, doing all the calculations just like before. Here Alka was hoping for at least double the performance improvement because we were using 2 Go routines instead of 1. But on the quite contrary, the runtime increased by more than double. It was about 4 minutes and 42 seconds. And we were using an unbuffered channel for this. So I told her to quickly change this to a buffered channel and see what happens. Changing to a buffered channel improved the execution time by a bit, but it was still slower than even our first attempt. So what happened? This happened. Alka was not able to understand even 10% of the nodes that are present over here. Because these are not something that represent what we had written. These are not the functions that we had written over there. The problem here is, if you look at the big box at the bottom, it suggests that our Go routines were sleeping for about 220 seconds. This muddled the whole concept of parallel understanding for her. So she spent a couple of days reading about concurrency, parallelism. She went through a lot of blogs trying to understand huge volume of data ingestion. She went through this profile again and again. And then she told me that she has found the issue. So the problem was that we were reading one line at a time. We were pushing it one line at a time on the channel. And since we had very small lines, and there were a billion of them, our program spent most of the time doing Go routine synchronization instead of doing actual work. So the solution here that we decided upon is to batch up these lines and then put on the byte channel. This means that we have to jump back to reading again. So that's what we did. And while we were looking into the scan methods implementation, it was just like bytes.split. It handled a lot of scenarios, a lot of edge cases, again, which we didn't want. And it was using the same reader that we provided to it during its object's construction. So we decided, why not call that reader ourselves? So we created a small POC, and we read the whole file using the file reader. And it read the whole file in about 11 seconds. And by this time, Alka had read up about buffer sizes and how they impact your program in terms of data reading. We saw that by increasing the buffer size, we were able to increase the performance of our reading part, but only up to a certain limit. If you go beyond that limit, your performance drops. For this particular application, our sweet spot was 4 megabyte of buffer size. But then another problem arose. Since you are reading data in chunks, it is very highly likely that one of the lines, actually the last line is going to be cut off at any position possible. So if you look at this example, we were only able to read up till D, E, and MA in the first buffer, and on the next iteration, the program read from RK semicolon and so on. So we wanted to read, process all the complete lines, but we also didn't want to neglect these cutoff lines. To prevent that, what we did is we created a leftover byte array, which would capture these cutoff lines, and then on the next run, or rather the next read, it would prepend it to the buffer, and then that line would be whole. This way, we were able to read the whole file in just under 4.6 seconds. Now that our reading was sorted, we could jump back to processing again. We used this new reader in our single-threaded program, and we saw that the whole program ran in about 1 minute and 1 second. But while we were experimenting here with the buffer size, we saw that reducing the buffer size improved the performance in this particular application. This brought our runtime to less than 1 minute. Now you may say that this is very weird because 2 slides ago, you just told me that increasing the buffer size made more sense, but now decreasing it does so. Why is that? So what happens is that your code's runtime has to take trade-offs between your memory pressure and your number of syscalls. Smaller buffers would mean a lot of syscalls, but would reduce the memory pressure. On the other hand, larger buffers would mean lesser syscalls, but bigger memory pressure. So as a general guideline, when you should always benchmark with different buffer size for your particular application that you're testing, because depending on the way that you are reading and then consuming your data, this buffer size would vary a lot. And it depends on a host of factors like your CPU's architecture, your RAM, your L caches, your operating system, your current memory pressure, and so on. Now that our single-threaded application was working fine for us, it was time to make it parallel again. And again, to start with and to check if we were not creating some Go routine overhead like we did last time, we created just one reader and one worker. This further improved our execution time to 56 seconds. And even better, it didn't create much problem for us like it happened the last time. But then, when we profiled this, we saw that around 50 seconds were spent in this pthread const signal, which meant that our application was doing a lot of weight group synchronization. Since our reader was quite fast and we had data available in batches to process, we thought that by increasing this number of workers, we would be able to reduce this time spent on pthread const signal. And I should tell you that at this time, our memory usage was about 23.5 gigabytes. And for this particular application, increasing the buffer size again from 64 kilobytes to 512 kilobytes made more sense and reduced our execution time to 55 seconds. So now we increase our workers. We made it equal to the number of cores that we had, which was 8. And we distributed workload to all the workers and then gathered the results to print it out. This massively improved our runtime, or rather the execution time, to 12.3 seconds. And over here, the buffer size that was the sweet spot for this particular application was about 1 megabyte. This brought down our execution time to 11.74 seconds. If we increased it further beyond 1 MB, the performance used to decrease. And if you see from here, this program was pushing our CPU cores quite hard. And our laptop used to get quite hot a lot. And since we were using a fanless laptop, this was even exacerbating the situation. So after every run, we had to wait for some time because we wouldn't be able to understand if the performance changed because our CPU was being throttled or because we changed the code. So again, as a general guideline here, you should always consider these external factors that affect your program, because your process is not the only process that is running on your system. So consider these noisy neighbor processes, consider your CPU throttling, consider this fluctuating latency in your network, and other things as well. Since our application was almost done, we tried to play a little bit with garbage collection. And since garbage collection is a program that takes up precious CPU resources, we turned it off. But our memory usage at that point was greater than 22 gigabytes, and our RAM was only 16 gigabytes. So Alka suspected that our program is going to crash because of out-of-memory error. But thankfully it did not, even though the runtime increased to more than 22 seconds. And that's when she learned about swap memory and and she was really amazed at how your operating system handles all these different scenarios under the hood. Since this turning it off didn't work out for us, I suggested to her that why can't we tune this garbage collector? So we decided to decrease the frequency of these GC triggers. And we found out that by using this set GC%, we were able to reduce the frequency, and this brought our execution time to 10.55 seconds. When we profiled this application, we saw that this single line was taking about, and this is a heap profile, we noticed that it took about 9.05 gigabytes. So we wanted to improve on this, and this happens because when you typecast a byte array into string, and since strings are immutable in Go, the runtime has to make a copy of the underlying byte array to provide us the backing array of the string. So that's when we bumped upon unsafe strings. And this, in a way, bypasses the safety of your language. This helped us to prevent this copy of byte arrays. And from the name itself, it suggests to you that you should not use this in production unless you're very well aware of what are its consequences and what you are doing. By using unsafe strings, we were able to reduce our memory usage by 9.05 gigabytes, and it brought down our execution time to just under 10 seconds. At this point, Alka was quite satisfied with all the achievements and the improvements that she had made, which we have plotted over here. And if she was here, she would have told you that this challenge was a real eye-opener for her, because we learned about mechanical sympathy. We learned that how different buffer sizes affect different programs differently, how zero-copy string conversion helps us to save some precious CPU times. We also learned the coveted art of profiling and benchmarking. And to be honest, without these two, I don't think we would have been able to proceed further even from our first attempt. We also got some exposure to garbage collection and how it affects our application, both in terms of CPU cycles as well as memory. I should also mention that we took a lot of trade-offs over here. We sacrificed code readability and maintainability for the sake of performance, because we practically modified every standard library code for ourselves. And you may not need these deep optimizations every day in your work, but I still urge you to take up this challenge because it teaches you so many things that we as application developers tend to ignore a lot and take granted for a lot. So these are the pointers where you can start from. And I would love to talk about the further optimizations that you guys come up with. You can reach out to me on LinkedIn and Twitter if you have any questions, if you want to discuss something. And all the code that I talked about is present on this GitHub repo. You can run it for yourself and see what all happens in your particular system, because this whole thing is very contextual. And at One2N, we have created an awesome Go bootcamp where if you want to solve real-world challenges and if you want to get better at solving them, here's the QR code for that. Thank you. I can take up questions now.
I'm supposed to say if you can go to the bar and ask for questions. Silence in the audience right now. There you go, the first question. Short.
Hi. I just had a question, like when you talked about GC optimizations, did you consider using sync.pool to create that byte buffer?
Yep, we did, and this even reduced our performance. Oh, I can talk to you regarding that. We can sync up later.
Thank you.
Yep.